When applying deep learning to healthcare, we are faced with many challenges. One major challenge is those regarding data. Um, in this presentation, we are going to study some of these data-related challenges. I've categorized the data-related challenges that I'm going to talk about into two sections. One of them is nature of observations, and the other is partial observations. Partial observations can occur in multimodality setting where we have missing modalities. So yeah, let's get into it. First, nature of observations. Some of the challenges of nature of observations are extreme imbalance with respect to ROI. What do I mean by this? One big difference between using deep learning with natural images and medical imaging is that with natural images, oftentimes the object of interest is very large and usually in the center of the image. However, in medical imaging, this is not the case. In medical image data sets, this is not the case. In the figure to the left, the nodule consists of less than 1% of the entire image. So this is what I mean by extreme imbalance with respect to our region of interest or ROI. Another challenge facing medical images is small data sets. So medical image data sets are usually orders of magnitude smaller than vision data sets. And as we discussed before, deep learning performs poorly in low data regimes. Another challenge would be distribution mismatch. So there's usually a distribution mismatch across data gathered from various hospitals. This could be due to noise in data acquisition, different image reconstruction algorithms, or hardware specifications. And this is usually the hardware noise from hardware specification is usually very evident in MRI data. So let's go through each one of them one by one, starting with extreme imbalance with respect to region of interest. So let's go through some of the solutions we can have. One solution for extreme imbalance problem is training with patches instead of training on the full image. This allows us to create balanced batches for training. And also an advantage would be that if there are places in the image which we think are more important, we can make the model pay more attention to those regions by oversampling patches from those parts. For example, regions around the tumor border or the edges of the tumor are more important because they represent discriminative features which usually the model needs to make a correct classification of the image. For example, in segmentation, we can oversample patches with high entropy in the label space. What I mean by that is that patches that have multiple labels. That's what I mean by high entropy in the label space. Why would we want to do that? Because those patches represent edges, and we want the segmentation model to handle edges better. So a case study that I would like to share with you is a paper that we published back in 2015. And this is for segmentation. And here's the problem setup. Now we have 4 MRI modalities, namely T1, T2, T1 contrasted, and FLAIR. And we want to use these 4 modalities to train a segmentation model which can segment the tumor and its sub-regions. Now, because the tumor is very small with respect to the entire image, instead of inputting the whole image, we do it patch by patch. We do training in two phases. Right, we do training in two phases. In the first phase of training, we sample patches uniformly over classes. This allows us to learn features that are not sensitive to the distribution of classes in our data set. So uniformly sampling patches over classes means that consider a batch of patches. Now, in the patch, in that batch, all the classes are equally represented. We don't have more patches from one class and less patches from another class. This is what I mean uniform sampling over classes. Now, in the second phase of training, there we go. In the second phase of training, we freeze the feature extraction layers and only train the classifier on a distribution that is closer to the true distribution of classes. What I mean by that is that we sample more patches from the healthy class and less from the unhealthy class. And even in the unhealthy class, we sample more patches from, for example, classes that are more probable in the data set. For example, the green class in the image that I showed you, because it occurs more, right? So this is the second phase. This way, the classifier has a better knowledge of the prior probability of each class. Now, because the model is fully convolutional, at test time, we can just pass the entire volume image to the model, and it produces the segmented 3D volume. So while training is in patches, the inference is in full image. This also helps with memory concerns. So we don't need GPUs with high amount of memory to train our model. Right, so okay. So here's how the training progresses over the first and second phases of training. We trained the first phase for about 60 epochs and the second phase for only 10 epochs, since the feature extractors are already frozen and they're already trained. So we only need to train the classifier. It doesn't need a lot of second phase, doesn't need a lot of training. So as you see in the second phase, training the second phase actually helps removing a lot of false positives, which occurred by the first phase. Because in the first phase, the model thinks all the classes are equally likely, since we trained the model with equal number of patches from every class, right? In the second phase, we introduce a prior by sampling patches according to a distribution which is closer to the actual distribution of classes in the data set. In the bottom figure, now also in the bottom figure, you see some segmentation examples produced by our model in 3 different views. Even though the segmentation is done in 2D, the 3D look of it is very coherent, and it doesn't create any artifacts. Right, so using this model, we took part in Brat's 2015 challenge, the Brain Tumor Segmentation Challenge, which happens every year in conjunction with MICAI, which is a medical imaging conference. And we did very well, and we were among the winners of that challenge. Right, so also, yes, so a paper from a colleague of mine at Imagia extended the patch-wise training with curriculum training, which means you first start the training on easy patches. So it's again patch-wise training, but you start the training with easy patches, and as the model gains more knowledge about the task at hand, you increase the level of difficulty by introducing more challenging patches. So they actually applied this on long nodule detection, and easy patches were patches which contained large nodules, and difficult patches were patches with small nodules. Using this method, they achieved a state-of-the-art in nodule detection task, and there was a challenge about it as well. It's on LIDC dataset. Right. So another way to deal with extreme imbalance with respect to region of interest is using a pixel-wise weighting loss function. This works well in segmentation applications. So instead of doing patch-wise training, you do a full image training, but then you impose weights on every pixel in the image. So the famous paper unit used this technique, and here the WC is the class-wise weights, and W is the pixel-wise weight. We are saying that this essentially using weights here means that every pixel has different amount of importance, right? So in their case, every pixel is weighted by the distance it has to the two closest edges, which are designated by D1 and D2. Using this technique and also other components in their method, they achieved state-of-the-art in multiple segmentation tasks. So yeah, so this could be an alternative to patch-wise training. And come to think of it, they're actually equivalent, because the more you introduce a patch, you're actually increasing its importance in the training procedure. And here, you don't increase the introduction of a patch. You don't oversample a patch, but then you increase the weight it has in the loss function. So, come to think of it, they are equivalent in some sense. So if there are any questions, I'll be happy to answer.